like screen sharing. Not on the screen.
Hi, folks.
the virtual audience can hear me, they can see my slides, and we can get that reveal workshop up and running again. All right. So hi again, everyone. My name is Maria Di Macapulo. I'm a senior marketing over at Spotify, leading two teams that rank and assemble the Spotify homepage of every Spotify user. I'm very among all of you in person, minus the 3 years since the last reveal, and it's so good to have that energy back. We have to get in that virtual plus live world. Energy of being in person with you for anything. It feels like yesterday since last reveal. Okay, so today I'm going to talk to you about the topic of causal adaptive learning for recommendations. And over this talk, we are going to review work collaborators and I have done over the years in the intersection of adaptive learning and causal inference. So first, to get what is adaptive learning. So an adaptive learning agent, for instance, the home recommenders, interacts with the Spotify user. And the agent learns from these repeated interactions with the environment. First, it observes the state of the environment. In our example, it's the history of interaction. And the agent takes an action, such as Spotify's homepage. And finally, the agent observes a reward of both the state of the user as well as the action that the agent took. And more formally, in adaptive learning, in order for the agent to learn to the value function estimation problem. So more formally in adaptive learning, we define the concept of a value function, which really captures A from state S. And this value could be representing an immediate reward, for instance, what is the user's engagement within a certain session with Spotify, or it could be something like a long-term reward. What is the cumulative reward over the user's banded adaptive learning problem, whereas if the value function represents the reinforcement learning version of adaptive learning. In contextual banded value function is estimated by individual state action reward observations, whereas in the reinforcement learning, we estimate the state action value function from state action reward trajectories. And after estimating that state action value function, the agent now has to balance what we call exploration with exploitation, meaning that in order to find the optimal policy for that environment, it needs, of course, to take actions that maximize the estimated state action value function, while at the same time, it also needs to take actions that explore the action space, particularly to estimate accurately the state action value function spaces of the state action space that have not been explored much. And ways to balance this exploration versus exploitation, one approach is the epsilon greedy, where the agent takes the optimal predicted state action value function with probability 1 minus epsilon, and then with probability epsilon, it takes a fully random. Then we have the upper approach, where confidence intervals on the state action value function and takes the action that maximizes the upper confidence interval of the state action value function from that state. And finally, we have the Thompson sampling version of operation versus exploitation, where the agent forms a distribution over the state action, samples from that distribution, and takes the action that maximizes that sample. So as we see, state function estimation lies at the heart of every adaptive learning agent, every adaptive learning algorithm. And in order to get decision-making right in practice, first we have to get the state action value function estimation right. Now, we're going to discuss about estimation in decision-making in actual bandits, but the concepts as well as the methodology that we're going to into the reinforcement learning domain as well. But if we look at the contextual bandit setting, traditional contextual bandits estimate that state action value function with action, information, it over the immediate, and they train a model to learn the parameters, theta, of the state action value function. And the way the state action value function is estimated is by minimizing the prediction error. So for instance, when we have a continuous reward, we will have the minimization of that loss function over here, the mean squared error minimization. But if we think about it, this is a prediction formulation. We are going to try to find and predict of the value function from a state and action. But if we think of it, asks an inherently causal question. It asks what versus another. Really, it hones into the differences of actions, whereas the pure prediction formulation doesn't. So in order to get adaptive learning estimation of state action value functions, we really have to focus on the causal effect and simply think about it as a prediction problem. And if we think about state action value function estimation as prediction versus causal effect estimation, in fact, decisions may break to various reasons. One reason why it could break is due to selection bias in the data. The fact that all learning creates progressively unbalanced training data sets. And that's a natural thing for the agent to do over time, going to sample some actions more than others. Is going to sample more actions that are predicted to perform well. So automatically it's going to create an unbalanced training data set. That's its nature, but that action value that can pose problems in the estimation piece. And also decision making may break due to what we call regularization. It could be something very explicit with the model imposing an L1 or an L2 norm regularization, but also regularization in this type of estimation problem can be implicit. State signal that is much more predictive of the immediate reward than the action signal, which is quite common. If we think about it, what is more predictive for the user's future engagement? Is it like the single item that the recommender recommended, or is it interactions of the user with the recommender? It's the state signal that carries more predictive power by the state signal and not the action signal, where in fact the adaptive learning agents, what it cares of its action. And of course, these issues can be exacerbated in the presence of model misspecification, we call it. So when the reward model of the agent departs from the true data generating process of the environment, that's very natural. We do not know the true reward data generating process in our environment. Also break due to covariate shift. So when the user distribution changes over time. And again, this is something that we also see in practice when, for instance, there are early adopters who interact more with the service at the beginning, and then their interactions are taking effect the entire user base. So in our 2019 paper with Susan Athey, Guido Imbens, and Zeyuan Zhu, we proposed a different contextual bandits that we call replacing standard model estimation that lies at the heart of every contextual bandit with important sampling weighted. What does this mean? Every time an agent takes an action from a state, it takes action with some probability. In the case of an epsilon greedy agent or a Thompson sampling agent, we know exactly this probability. Even in the case of an upper confidence from the historical data of the agent. So every state, the agent takes an action with a certain probability, and we know the propensity score, and we know the policy of the agent. So beginning of the model, instead, now we weigh each observation propensity score in order to estimate parameters of the state action value function. And the question is like, what's behind that is that within first propensity score weighting, within spontaneous sampling weighted training, we're going to avoid rare observations And that will make the action selection of the agent as good as random. By doing the importance weighted training, now the action selection will look as good as random. Policies in online adaptive learning agents, we know the propensity score, and even if we don't know the reward model accurate, that we know the propensity score give us this doubly robust property of the guards us against the selection bias. Intuition about why it works. Let's look at the simulated user embedding reward surfaces of 3 actions. Blue podcast. And if we zoom on that part of the state space, say we state space, now the reward surfaces are going to look mostly flat. So even though in the global user space, the red space, things look a little bit different. So now we compare in a standard of comparing the importance sampling weighted bandits with traditional bandit approaches such as the linear Thompson sampling, linear UCB. So over here in these figures, we saw the progression of the action selected by the agent. And we see that very traditional baselines, such as linear Thompson sampling with model misspecification, the fact that they're using a linear model instead of the quadratic reward surfaces that we saw earlier, as well as this covariate shift, this early adopter to more entire user-based shift, we see that they have trouble identifying that the optimal action vast majority of the user space is the red podcast, and they identify the yellow action. Whereas Thompson sampling paired with importance sampling weighted training, very biased due to the covariate shift and the selection bias in the data, and identify what is the optimal action for a big part of the user space. Something very interesting here is that even if we incorporate importance sampling weighted training on deterministic exploration approaches such as UCB, again, the results are not as good as when paired with probabilistic exploration. So UCB deterministic approaches have a tendency of assigning whole parts of the state space on the same action, so they cannot make the most of that upweighing of rare observations due to the deterministic nature of them. So for better guarding towards model misspecification and covariate shift, that combination of importance sampling weighted training with probabilistic Thompson sampling exploration is what will guard us best. Now let's move on whether we can do better than importance sampling weighted training. We're training the adaptive selection. At the same time, in sampling weighted training comes at the cost of higher variance, particularly when these propensity scores become small, which again is natural as the agent progresses with its learning. And apart from paying the high variance price, also importance sampling estimates lack asymptotic normality. So we see here that inverse propensity score weighted estimates, as well as an augmented version of inverse propensity score weighting, fits the model of the reward first and then applies the propensity score on the difference of the reward with the predicted reward instead of applying it to the entire reward. The variance a little bit, it has lower variance and importance sampling weighting from large variance when the propensity scores become small. And why do we care about asymptotic normality? But particularly when we say we have Thompson sampling, that asymptotic normality is a desirable property to have when we're building adaptive learning agents with optimism in the face of uncertainty exploration. So very often we rely on that assumption of normality. So In 2019, Susan Nathan's group proposed to stabilize the variance of a doubly robust estimator by, instead of giving an equal averaging of every observation to the final estimate, now this estimator weighted each observation final estimate. And they chose an adaptive weight 1 over square root property, and they proved that this is unbiased and asymptotically normal, but this result was only applicable for unpersonalized policies when we don't have the contextual information. So in our 2021 paper with Aurélien Bibon, Nathan Kalus, Antoine Chambaz, and Mark Mardelan, we extended that work into the contextual bandit setting. And the estimator we propose is, again, a contextual adaptive doubly robust estimator. It looks very similar as the non-contextual information everywhere. What's most complex is how do we estimate these adaptive weights to stabilize the variance when we have contextual estimation. So in that case, these adaptive weights should still be inversely proportional than the variance this term contributes, and we estimate the variance of that term using importance sampling. Actual adaptive doubly robust estimator ended up being an unbiased and asymptotically normal estimator, both in the case where we have non-contextual policies, as well as in the case when we have compared in a large-scale empirical study how contextual adaptive doubly robust estimator does in terms of coverage of the ground truth. If we estimate the collected by a contextual logging policy, how often will the popular baselines in offline evaluation literature, such as direct method, DW, those cover the ground. And we used public classification data sets. We converted them with partial feedback by only revealing the reward of the chosen class than every class in the observations. And through these 50 OpenML data sets, we compared the various estimators, and we saw that the contextual adaptive doubly robust coverage tends to be higher than all other baselines. So y-axis, we have the coverage of the contextual, and on the x-axis, we have of the baseline. So the higher, the better. And when we're at the top left part, it means that the contextual robust estimator has 50 data set. And this you start a tree-based policy, evaluated like a tree-based target policy, on contextual data, we can coverage of the ground truth. So the final question we ask is whether we can transfer back this learning to the online setting instead of having now only the offline estimation part. How do we get unbiased, asymptotically normal estimation offline? Learnings of the adaptive double robust estimation when we build online learning agents. And the adaptive banded, but instead of having the standard Bayesian posterior at its center, it was getting a normal posterior coming from the adaptive doubly robust estimator. I think someone may not be muted on the Zoom. Maybe live questions. I'm taking live questions. Okay, thank you. All right. No worries. But yes, the doubly adaptive Thompson sampling algorithm suggested replacing the posterior at the heart of a Thompson sampling learning agent with a distribution stemming from this adaptive doubly robust estimator we introduced. So the posterior mean was the mean of the adaptive doubly robust estimator. The posterior variance was the variance of that adaptive doubly robust estimator, which can also be estimated in closed form. And now we could take this as a posterior, as a normal posterior, because we have proven that by construction, adaptive doubly robust estimator is asymptotically normal. So it pairs really well with the Thompson sampling exploration. And the intuition about why robust estimation learning data collection, everything we talked about for the first part of the talk about why important sampling weighting training is important learning agents, so the robust estimator gets that. And also the adaptive doubly robust estimator now is asymptotically normal. It will vary with some sampling based exploration. So indeed, the doubly adaptive Thompson sampling algorithm performed better in practice, as we will see in the final empirical evaluation, and also matched the state of the regret bound that standard Thompson sampling has. So indeed, in that simulation study, we tested from like small to mid-sized action spaces, 5, as well as high noise and low noise settings, and the adaptive Thompson sampling variants, both the one that has a and the stick that imposes propensity score clipping, lower regret, meaning they were achieving higher reward, and the green lines over baselines. And also doubly adaptive Thompson sampling able to have higher stopping power, meaning that they can identify the optimal action with fewer samples than the counterpart, the vanilla Thompson sampling. We wanted to see if these results would be transferable the domain to a practical domain. Did they were? So this shows evaluation. And again, the doubly adaptive Thompson sampling, is performing both the baselines, Thompson sampling and UCB, but density score weighting or Thompson sampling with doubly robust. What this shows bias correction due to adaptive data collection, as well as the asymptotic normality property that is going to work best in practical scenarios. So double Thompson sampling covers reward, but also it can identify the optimal action faster. So to conclude, what we cover is that estimation is at the heart of any adaptive learning agent, yet state action value function estimation right. But there is a lot of challenges that we are faced when we are doing adaptive learning estimation. In the online setting as well as the offline. And the best way has worked so far is to combine exploration, online learning agents such as Thompson sampling. And this is what in practice while achieving state-of-the-art theoretical guarantees. So I'm going to thank you for your attention. We're going to get questions at the end. Thanks.
About modeling user preferences using our first observable mark of the problem for reinforcement learning sequential aware recommender. Roy is a group is coming up. And as Maria mentioned, we'll be holding Q&A towards the end. And of course, if you're attending live or in person, we have a poster session. And if you ask your questions via the Zoom chat, the speakers can answer them async or answer them directly virtually. So with that, let's get started and move on.
So hello, good morning, everyone. Myself, Ayush Singharoy. I'm a PhD student at UC Dublin. And today we'll present some initial work on modeling user preferences using a partially observed Markov decision problem for sequence-aware recommender using a reinforcement learning framework. So this work has been done with Ingus Lawler and Neil J. Hurley. So first we'll move on to introducing or mentioning the sequence-aware recommender. And here we see that in many real-world recommender system applications, we are required to recommend a set of items to serve the user's needs. So in these scenarios, dealing with the sequential information becomes an important task. So suppose if we have a set of C items and a set of I recommendable items, the goal is to compute an ordered set of object L, so that which is of length K, and that each item in the object L belongs to the item set. So technically, each sequence L is an element of the set of all permutations. So possibility we can have the all permutations of K length. Now, going towards the problem formulation. So the focus of this work has been to recommend a sequential recommendation of ordered lists. So in this, the input is the sequence of lists offered and the past feedback given by the user. So in this problem setting, we define the session as a set of K items, and the feedback is received from the user for each item in the session. So suppose that there are total number of N items. The nearest way of dealing with this would be to have an N to the power K sessions, because each recommended items has N options. And for that, we learn the user preferences towards each of the N to the K sessions. But sometimes it turns out to be infeasible for large state spaces. So in this way, modeling the user preferences individually toward each of the N items would be a better way to go off. But then again, it comes along with its own challenges. So we go for an reinforcement learning based scenario in this framework. And for that, suppose the action, we define it as any item which the user is interacting with, and the state space here is a set of observable state spaces like the user description and others, while the hidden states are the user preferences towards each of the items. And the reward is most of the user feedback, where it's kind of like, dislike, or the user satisfaction, or the diversity of the sequential recommended task. And the environment is the end users and any of the web service app which we are using to recommend the items. So the above problem formulation can be set in different scenarios, like we can use it for recommending of music playlists, or a set of exercises, or a set of training courses. So in this, we define the episode as a sequence of items for the session, and the model so interacts with the environment for n steps of that episode. And based on the observation, we receive an action and then receive a reward. And the ultimate goal is to learn a policy so that it maximizes the cumulative reward. So this is the reason why we move towards the reinforcement learning framework. So here we define how we have the state representation and reward function for our reinforcement learning framework. In the state representation, we have the user description. So the user description in this case consists of the user preference per item, which is the non-observable states in the real world scenario, and the user information, the user session objective. While if we serve it as a music playlist recommendation, then we can have the listening history, which consists of the session items, the session genre preferences, and the past session histories, and also the feedbacks. And while the reward function comes with different functions of the session diversity, the genre diversity, and the user satisfaction towards the session, and what is the user goal. So in terms of like training courses, it might be a goal which we have to serve to the user, like some kind of end session goal, and that's how we compute it. So here we have an RL framework, which consists of a gym, which is a user simulator to simulate end users for which the recommended items are recommended. So it has the user description, the learning history, the feedback, and it consists of the state representation and the reward function. So the restart function serves a new session for every user, and the step function makes a recommendation to every user. So the thing is that in real life scenarios, the preference of users towards each state, in this case, towards each of the items is unknown. And so we need to make observations or perform a belief over the state space. So there we have this belief function, which corresponds to the probability that the current state is S. So there we use the POM-DP, which is a partially observed Markov decision process. And the way it is different from a Markov decision process is that it gives us the observations and the observation probability. So it has an observation function and through which we learn the observation probabilities. So the agent receives an observation of the current state rather than the true state. And using the past observations, it builds a belief over the underlying state, so which can be represented as a probability distribution. So we just mentioned the POM-DP more formally over here, which is the set of states, actions, transition functions, rewards, but then the set of observations, the observation probabilities, and the discount factor. So the belief update here takes place like when, as it is a Markovian problem. So therefore, maintaining a belief over the state only requires the knowledge of the previous belief state and the action taken and the current observation. So we have a POM-DP framework, which has been mentioned by Zhang et al. Explicitly. And in that, what we do is that rather than learning a policy, we learn the belief over the state space. So if the agent plans an action A, then there is a transition function for which then we receive an observation and a reward, and then we update the belief given the action and observation. It has various POM-DP solvers like the value iteration, the upper confidence bound, and the POM-CP. But going towards this POM-CP, what we see is that as it's a large state space, so iteratively updating the observation over the whole entire state space is infeasible. So the advantage of using POM-CP is that it has this particle filters. So it has a collection of k particles, suppose which is the state in this case. And so each particle represents a probability of 1 by k. So suppose that state is observed x number of times, n number of times, then the probability updates of that state is to n by k. And the new state is added to the belief only if the observed observation matches the true observation. And this is done iteratively until we retrieve the k number of particles. So as we go through the initial results, at present, the user simulator enables 3 modes of learning. The first mode is that where we completely ignore the non-observable states and we deal with the observable states, while there is a full state representation, which is explicitly run from the gym. And then we use a state representation, which is run outside the gym through a POM-DP. And the initial results, which serves as a motivation in this work, is that the modeling the user preferences, the state representation using a POM-DP serves better than learning explicitly from gym. And the ongoing work, and which is we are working on, is to integrate the POM-DP within this framework. And the main again comes to the evaluation. So we want to assess the quality of recommendations on real users, and as we are consist of a different reward functions, which consists of the diversity, the goal of the session, and the genre preferences. So we also work on the reward optimization techniques for further evaluation. So that's it. It's kind of the initial work which we are further plan to extend on this RL-based framework. So I would be happy to have suggestions and questions during this workshop. So thank you.
Thank you so much, Ayush. I don't believe we have any, I don't believe that we have any questions specific to this talk within the chat, and we'll hold them towards kind of the end of this general session, just in case anybody in the room or anybody online has questions. Again, as a reminder, please make sure to add them to the Zoom chat. We will have access to the recorded sessions on the website after the conference is over and after the workshop is over. However, given the issues with the audio, we want to make sure that we have sort of high quality video and audio posted on the site. So we might be a little bit delayed for the first and second talks, just because there were a couple of issues with the audio. Next up, we have, let me pull up the agenda. Next up, we have a talk from Diana, who I believe will be presenting virtually.
Hi, everyone.
Diana, do you, excellent. Are you here? Yes, perfect. So we very much look forward to learning more about sales channel optimization via simulations based on observational data with delayed rewards. Please feel free to share your screen and we can give you presenters' rights.
Okay.
Excellent.
Oh, sorry, it's asking me to open systems preferences. Just a second. Oh no, I need to apparently quit and reopen for some reason. Can I have just a second? Sorry about this. Hi, I'm back. Can everyone hear me? Yes?
Yes, we can hear you.
Okay, sorry about that. For some reason, my Zoom is acting up. Can you see my screen?
Yes, we can see your screen.
Okay, all right, let me start my presentation then. All right, so thank you for having me. I'm Diana Negrescu from LinkedIn, and I want to talk to you today about our sales channel optimization problem at LinkedIn. To give a quick shout out to my team, in particular Pasha Khosravi, who's a PhD candidate at UCLA, and he implemented most of what you are about to see during a summer internship at LinkedIn. The agenda for today is, as you can see here, I'll dive right into the problem. The sales channel optimization problem is one that's commonly incurred by many organizations who are trying to figure out what is the best way to reach out to potential customers, referred to as leads, while having a fixed set of channels to do so. And each channel carries an unknown likelihood of success that we're trying to learn. In particular, for a LinkedIn sales solution product, we have 3 customer acquisitions channels that are available. The first channel, let's call it channel A, involves online communication, very little manual effort, it's highly automated, and we have relatively short time to feedback, typically in the order of tens of days. Another channel available is channel B. This one involves a lot of personal communication with the goal of establishing a long-term client relationship, and therefore the time to feedback in this channel is very long. Lastly, we have channel C available, which strikes a balance between channels A and B. So it involves less effort than B, but brings longer delays than channel A. So the time to feedback here is medium, measured in a matter of a few months. There are a few challenges that I should probably mention here. So in general, of course, when training data is available, so in our case, we have data on the features of each account that we want to allocate, historical channel allocations with their outcomes and recorded delays, we can typically build data-driven policies. And of course, it's best if the training data that we have was collected through randomized experiments. But of course, in many cases, and including ours, experiments can be risky, expensive, or time-consuming. In particular here, where 2 of the channels especially have very long feedback delays. And so what ends up happening in practice is we rely on observational data to inform our policies. And as we know, observational data suffers from various forms of bias, and that raises the question of suboptimal performance of models trained on it. So how should LinkedIn reach out to potential leads? Historically, the way this has been done is through rule-based policies where a set of features, or sometimes even one feature, was selected and deemed important, and then based on the values of that feature, the channels would be allocated. But of course, that raises concerns because the outcomes data also collected this way can suffer from selection bias, and therefore it can impact learning policies learned on it. So our approach here was then to develop a simulator in order to empirically study what happens as we, for instance, use randomized versus observational training data. What happens when we use different types of policies, varying from rule-based to supervised machine learning to multi-arm banded policies, and also what happens if we were to face different reward scenarios, so different ground truths or varying delay distributions. I will maybe skip through the related work since you've already seen much of it today, but I just want to mention that there's a growing body of work in off-policy learning and also multi-arm bandits. Here we focus on empirical evaluation of some simple policies in the problem constraints faced by LinkedIn. Okay, so the problem setup here is we adopt a contextual multi-arm bandit framework where at time t, we're given an account that's described by a feature vector xt, and we wish to allocate this account to one of the available channels, right? So the action set here at LinkedIn in particular is one of the 3 channels A, B, or C. And given this allocation, we would observe a reward, R of XTAT, which in our case is binary. So 1 means converted, 0 not converted. And we observe this reward after a random delay tau. And I just want to note that tau here depends on the action, but also is not independent of the reward, unlike I think a lot of the assumptions that are commonly made in the literature. So our objective then is to maximize the expected cumulative rewards observed over a given time horizon t. Before delving into some more of the simulation details, I just want to show a visual of the data that we had available. So here we're showing some histograms by channel and by conversion status, so reward type. The main takeaway here is that the shape of these distributions can vary quite differently between these different channels and different conversion status, with, for instance, successes having a higher mass around earlier or shorter delays than not converted leads. Also, for instance, channel B having more mass in general over the longer delays. So some details of our simulation. So I mentioned that we had this data set from LinkedIn leads. So we built a discrete time simulation informed by this data set that contained over 200,000 accounts. We did some pre-processing, of course, and the main kind of decision points in our in designing our simulator were, first of all, how do we simulate the data collection? Which policies do we use? How do we simulate the observations or the ground truth? And also, how do we simulate delays? So to kind of take them one at a time, for data set collection scenarios, we considered three. The first one was a fully randomized scenario, which assigns channels uniformly at random. We also considered an observational scenario. So this is something that's in line with the historical rule-based policy implemented at LinkedIn, where we choose one feature, we call it F hat, and we assign channels based on the values of this feature. So if F hat's less than 10, we assign to channel A. If it's greater than 20, to B, and otherwise to C. And then we also considered a partially randomized scenario here for data collection, which is meant to be something sort of in between the first two, where we keep the actions the same as in the observational scenarios for feature values less than 10 or greater than 20, but otherwise we randomize between allocation to channel B and C. And this is something that was considered at LinkedIn to sort of not disrupt things too much compared to what was historically done, but also introduce some amount of randomization to have hopefully better data collected. All right, next, in terms of what policies to use from now on. So we simulated, first of all, the historical rule-based F hat policy, which assigns channels the same way as in the observational data collection scenario. We considered a supervised machine learning policy, XGBoost, which trains an XGBoost model on our simulated log data and then chooses the action with the highest probability of conversion. And as done in practice, it retrains the model about every 90 days. We then moved on to multi-arm bandit policy. So we also tried an epsilon greedy policy that epsilon% of the time allocates channels uniformly at random and otherwise uses the XGBoost policy. And finally, a simple multi-arm bandit policy, LinUCB, which chooses the channel with the highest upper confidence bound, assuming, of course, a linear relationship between features and conversions. And to note, this policy was online, so it updated its policy as new data became available. Now for simulating observations, we first used k-means clustering to aggregate accounts based on their feature vectors, and then developed three scenarios for simulating these rewards. The first scenario we call historical because we assign each cluster action pair a Bernoulli probability P that was computed as the maximum likelihood estimator on our LinkedIn data. Then we also consider here a uniform scenario where we assign each cluster action F hat pair triplet a Bernoulli probability of success that was uniformly sampled. And then we also considered something in between those two. We call that scenario F hat adjusted uniform, where we start off similar to the uniform scenario, but then we bump up the probability of success whenever the action F hat pair is the same as in the observational scenario. And this is to sort of bias the rewards to be more in line with the historical policy. We also tweaked the delays. So we wanted to see what happens under different delay scenarios. And so what we did is we sampled the delays from our data set, but we used a constant lambda to multiply those delays values by either 0 or 1/2 or 1 in order to simulate what happens under no delays, historical delays, or sort of half of historical delays. Okay, so now to move on to results. Here, for example, I just want to say the setup. So we simulated that data collection for 90 days, and then we let the policies run for a simulated horizon of 1 year. We looked at what happens under these different scenarios. In particular, we looked at the lift percentage, so the relative change in cumulative rewards compared to the historical rule-based F hat policy. So as we can see here in this plot, which shows the performance under different data collection scenarios. First of all policies perform better than the historical rule-based policy as we'd expect. Overall, LinUCB seemed to be performing the best out of the policies that we tested, and that performance gap seemed to be highest whenever the data collection was observational. However, LinUCB also performed well under the randomized data collection scenario, as you can see. And we varied these different scenarios. So I just want to briefly go over the other two, but the results were basically robust to different reward scenarios and also different delay distribution scenarios. So just to sort of wrap up, we found that our simple policy LinUCB tended to outperform the other policies by a range of 18 to 47% compared to the rule-based F hat policy. This performance gap was greatest whenever the data used for training was observational, but performance stayed pretty high even when it was randomized. These results were robust to various changes in reward distribution and delays. Looking at supervised machine learning policies like XGBoost, we found that even partial randomization does tend to help their performance. In general, multi-arm bandits seem to perform well regardless. So I know we're sort of short on time, so I will end here. I dropped here a link to our archive paper, and if there are any questions, maybe you can see in the chat. Oh, I don't know if we have time for questions now. I'll let the organizers decide that.
We definitely have time for a question, and if
Oh,
you and it looks like we have at least a couple added to the Zoom chat. So please feel free to ask the questions and then answer them for the in-person and for the virtual audience.
Oh, I see one question Did you try to decrease epsilon during the simulation? No, we did not. We just tried 2 different values of epsilon. So we tried value of 0.05 and 0.1. That's a good question. And then let's see, was there something else?
Yes, one from Hao Lee. So validating the simulation results.
Okay, that's a great question. Can we validate this with an actual A/B test? So there was somewhat of an attempt to try that. However, just to kind of reiterate the problem here, some of these channels have extremely long delays, up to a year, right? And so conducting A/B tests in this scenario is pretty difficult. From our partner team that we worked on this project with, I know that as a kind of a follow-up of this, they looked at the difference between the rule-based policy and the supervised machine learning policy. And they did find improvements there that were sort of consistent with our results, but we don't have full-blown A/B testing available, again, because of these very, very long delays, especially in channels B and C.
Excellent. Thank you so much for answering the questions and for a really delightful presentation. And thank you to all of our speakers for, and thank you for all of our speakers today for you know, your excellent talk and your work and sharing your knowledge with everyone, both in person and virtually. I think that we've gotten the AV issues at least somewhat hammered out, and I'm looking for wood to knock on to like make sure that that stays the case. And next up, we have a coffee break, a very short one, in addition to a poster session. The posters should be outside, so if you're attending in person, please feel free to make your way out, grab some coffee, grab some water, walk around, take a bio break, and we'll be right back and in person at 11:30 a.m. For our next selection of talks and our next invited speaker. So thank you so much today. And as we're all leaving, please feel free to give another round of applause for the folks that have presented. We really appreciate it and look forward to the next section.
There's no way for this header to go away.
There is. Boom.
Okay.
I just want to keep it up. All right, folks. Let's get our second session here started at Reveal and Consequences. My name's Justin Basilico. I lead the page algorithms team here at Netflix, and I'm really excited to introduce our next speaker, Edisham Elahi. He's a co-worker of mine at Netflix, and he's been there 10 years, which I didn't realize that you've already crossed that mark, which is pretty amazing. Edisham is an applied machine learning research scientist, where he's worked on improving a lot of aspects of the Netflix personalization and recommendation system over the years. He holds a master's degree in electrical engineering from the University of Michigan, Ann Arbor. And he's going to be talking about enabling reinforcement learning for RecSys with unit testing problems. So really excited to hear his talk. So let's give Edisham a warm welcome.
Thank you very much to the organizers for giving me the opportunity to speak about my work. So in this conference and even today's workshop, we have seen many talks about advancing the state of reinforcement learning, methodology, evaluation, etc. So my presentation is going to be a little different. It's going to be how we can make the application of reinforcement learning easy in industry, specifically using problems which resemble unit test problems. Okay, so let's get started. These are my amazing collaborators. Without their help, this work wouldn't have been possible. So as a running example for this presentation, I'll be using the slate recommendation task as the prototypical example. So just to define, slate is a sequence of recommendations, and the goal is to construct successful slates. So slate of recommendations that the users interact with. We can view this as a sequential decision-making task. So we can think of the some agent constructing these slates sequentially from top to bottom, and the users interacting with these slates also from start to end. Because of the sequential decision-making nature of the problem, we can ask this question: that can reinforcement learning help? And actually, like, I was very happy to see that there was an earlier talk which also talked about slate construction problem. So it's good that people are paying attention to it in reinforcement learning. So when we think about using reinforcement learning for this task, we can define like what the environment would be. So it would be the end user who would receive this slate of recommendations. The agent is going to be the recommendation model, and the action would be the item that the agent would recommend at a given slot in this slate. So let me tell a little story of an RL practitioner, essentially me, who was looking to apply reinforcement learning for this problem, for the slate recommendation task. So when I was thinking to apply RL for this problem, I had to go through these steps: hypothesis, data collection, modeling, and evaluation. You may wonder that these are typical for any recommendation problem. So what's so special about them for the reinforcement learning when we're thinking to apply reinforcement learning? I'll argue and I'll try to explain that they just get more challenging when you're thinking to apply RL for a task such as slate recommendation. So let's get to the hypothesis. So whenever we think about applying reinforcement learning, we need to answer this question: that why do we think that RL is useful for a problem? And the key to that question is that whether the dynamics of the environment, they are dependent on the action of the agent. Does the action that the agent takes can steer the environment into useful states that we think will provide us higher reward? If that is the case, then RL is an applicable solution to that problem. To further look at it in detail, so we can compare two agents. First one is an investment agent, which is making investment decisions, how much money to invest in a particular stock. So we can ask this question: that the environment, is that impacted by the action that the agent take, which is how much money to invest in a particular stock? Does that change the state of the environment, which is the entire stock market? Well, we can argue that if the amount of money is too large, probably it will change the state of the environment, but if it's too small, maybe not. Now let's compare that with our recommendation agent, whose goal is to construct the slate. And again, now the action that the agent is taking is recommending one item at a time in the slate. And we can ask the same question: that whether the recommendations change the state of the environment. In this case, the environment is the user. So does the state of the environment is influenced by the actions taken by the agent? We can reasonably argue that if, for example, if the recommendations are not good, they're not relevant to the user's interest, it will impart a negative effect on user state, and to the extent that it's possible that they stop their interaction with the slate and abandon. And similarly, like if the recommendations are good, it will leave a positive impression, and we may reap some benefits of that positive impact. So with that kind of reasoning, we can hypothesize that maybe RL is suitable for a slate recommendation task as well. So once we are satisfied with the hypothesis, we can go to the next step, which is collecting data. I can tell from my personal experience that whenever we talk about applying reinforcement learning at my company, Netflix, the conversation pretty much revolves around how we can solve the data problem more efficiently and in a less expensive fashion. Because data is more complicated for a reinforcement learning, for training a reinforcement learning model. So instead of just working with one set of observations, we need to collect a trajectory of observations, which include the state of the environment, the action, the reward, and also the candidate action. And tracking these trajectories and logging them can be expensive. And one aspect which doesn't get a lot of attention when I hear data logging talks or whenever people talk about applied RL is the candidate action. So if the agent is taking actions from some discrete set, this candidate action could be very, very large. And if each of the actions have a very large feature representation, so logging these candidate actions can be very costly. The third step is modeling. Fortunately, I've seen there has been a lot of progress in advancing the state of reinforcement learning models. There are some great models which are applicable to slate construction tasks, for example, DQN, reinforce, slate Q, etc. And many of these models have very good implementations available in popular software packages, for example, TF agents, RecSys, etc. So as an RL practitioner, I actually found it quite easy to experiment with many of them. And the whole question was that whether I can evaluate those models accurately, which takes us to the last part, which is evaluation. And I would argue that probably like doing a good evaluation for reinforcement learning is probably the hardest of all the tasks that I've mentioned so far. So even it's like really hard, but it gets easy when we can do on policy evaluation. So we improve the model. So in this case, we will generate new slates from the model. We'll show those slates to the user, get feedback, and then iteratively improve our model by repeating this cycle. Although like it sounds easy, but it can be very expensive from the perspective of that we are now generating slates from a possibly suboptimal model, because like if the model hasn't converged to a good solution, we will be generating suboptimal slates and then showing them to users, which can be a bad experience and could be inconvenient to the end user. So to get around that, off-policy evaluation is very promising, but at the same time is very challenging, because now we need to evaluate the entire list of recommendations that are being generated by some behavioral model under some new target model. And what we know so far is that evaluating one action in an off-policy fashion is really hard, let alone the entire trajectory that you have to evaluate when RL comes into picture. So looking at all these challenges, it can add lots of delays in when you're simply trying to apply reinforcement learning for as fundamental of a problem in recommendation as slate construction, or it can even deter or discourage the RL practitioner to move ahead and with the project, especially like when the upside or the benefit of applying RL to the problem is not known. So the question is that can we do something where we can sidestep these complexities and get some idea about the benefit and upsides of applying RL to a problem that is of interest to us? So fortunately, simulations and unit testing have been very popular in reinforcement learning, and I was very happy to see like many simulation-related talks in this workshop and the conference as well. And simulations and benchmark tasks, they have been very popular in reinforcement learning research, cart pole balancing, moonlander. These are the kind of benchmark tasks, we can consider them as unit tests as well, that we use to study reinforcement learning when in our courses and universities. So the idea was that can we define a simplified version of the slate recommendation task that we can treat as a unit test, and then we can like get some idea about the benefits or the upside of applying reinforcement learning on the slate construction task. So ideally, the task that we want to construct, it should be a confluence of ideas from simulation, unit testing, and benchmarking. So can we do that for the slate construction task? So the rest of the presentation is going to be the thought process that we use to define that task, so that if you have a similar problem in which you want to apply reinforcement learning, you can use similar thinking pattern to come up with a simplified version of your problem so that you can try to get a sense whether it's worth applying reinforcement learning or not. So, in order to design that task, we went to the first principles of reinforcement learning and asked this question that what is reinforcement learning supposed to do, let's say, better than a contextual bandit? And the answer is that reinforcement learning agent can take actions which make better trade-offs when trade-offs or tensions are involved between short-term and long-term objectives. And to emphasize that point, I again would like to give an example of a unit test slash benchmark task that we use in courses to study reinforcement learning, which is this mountain car. So the goal of this mountain car is to escape this valley, and the goal is on the right side where the flag is posted. When the mountain car is at the bottom of the valley, the optimal action is actually to back up the car, which is in the opposite direction of the goal, because doing that lets the mountain car build momentum, and then repeatedly doing that actually is able, the mountain car is able to escape the valley. So the point that I'm trying to make here is that the optimal action in a given state may look different or counterintuitive to the short-term objective, but that's the whole point of reinforcement learning, that it can identify those actions and then can do the overall task better. So for the slate recommendation task, can we think of introducing similar tension between the short-term and long-term goals? So I'll first go through the unit test task that we came up with for the slate construction, and then I'll try to convince like whether it has the right characteristics. So first of all, we simplified the state of the environment. Remember, the environment in this case is the user, to just one variable, which is, let's say, the budget of the user. We can think of the budget as a time budget. So imagine that the user comes to interact with a recommendation engine, for example, Netflix, and they have some kind of a time budget in which they need to make a decision. So, and then if we are unable to give anything that is of interest to the user within that time budget, we get a failed session. And so something like which is reasonable and relevant to slate construction task. And then we also simplify the representation of the item that the agent would recommend to only two features. One, which is the relevance, and I'll use star rating as stars just to show like the relevance of the item, and the cost. And we can again think of the cost in terms of time. So it doesn't have to be time, but like because I mentioned time budget, so we can think of the cost as also some kind of a time. And it can be the time that the user needs to understand a recommendation. To again give an example from Netflix, if we are recommending something like really popular as Stranger Things, the user may already be familiar with it, and the dwell time for user to understand that recommendation may not be that large compared to something which is new, but it could be relevant, but it's just that the time it would take to understand that recommendation would be large. So we can think of that having a higher cost. The item level reward in this unit test is going to be binary. And then users can only consider items that fall within their budget. So essentially the user browses the list from top to bottom. Each act of browse consumes from the user's time budget, and the consumption is basically equal to the cost of the item. And then when the user's time budget exhausts, they can no longer browse the recommendation. So anything that is outside the user's time budget, it's not relevant to the user. So in the next couple of slides, I'll try to convey the intuitive idea that how does that bring in the tension between the short-term and long-term goals that the recommendation agent is known to make better use of. So we have a user, let's say, and here I'll use budget in monetary values just for illustration. So we have a user that arrives that has a budget of $2. And for simplicity, let's assume that the agent has access to that budget. So it's basically just like saying that the state of the environment is fully observed, which is the case in Markov decision processes. So the agent has to make a decision which item to recommend at position 1. It has many options. In the first option, in the first slate, the agent can recommend a 3-star item, but with a cost of $2. Doing that will consume from the entire user budget, and then after that, any recommendation that the agent will make will be irrelevant. So, so that is like one option. In the second option, the agent instead can recommend a 2-star low relevance item, but with a cost of just $1. And then doing that allows the agent to recommend another 2-star item, which also like takes $1 and the entire budget is consumed. If we look from the overall utility of the slate, the second slate, although like each individual action has lower relevance, the overall utility of the slate is higher, 4 stars. And then in the third example, there isn't any compromise. Like in this example, the item has high relevance and low cost. But in the second example, like if the agent is considering that over the first one, there is a compromise to be made between the relevance and the cost. So that said, some of you may already have realized that this problem has strong connection with the 0-1 knapsack problem. So the connection is that the bag is of fixed size, and the size again comes from the budget of the user. And the goal is to fill that bag with the items that have the highest combined utility, and each of the item takes like some size, has some size requirement. So you cannot put all of them in the bag. And then your goal is to fill the bag with the highest utility item. And then knapsack is a well-studied problem. And then we explore more of that connection and give it a little bit more mathematical treatment in the blog post from which actually like this presentation is derived. Okay, so I hope with that illustration, I've made it clear that there can be some compromises to be made when it comes to the agent trying to solve the overall task. And then RL can be a useful technique to solve that problem. So the first step, so we go ahead and then try to apply reinforcement learning for this problem. The first step is to think about the problem as an instantiation of a Markov decision process. Again, we have an agent. The action that the agent take is to insert an item in the slot K of the slate. The item has a relevance and some cost. The environment is the user, and then they provide the environment provides a binary Bernoulli reward, which is proportional to the relevance of the. So the probability of getting a positive reward is proportional to the relevance of the item, and we only get a positive reward if the cost of the item is lower than the user's budget. And then the state transition is very simple. So we start with some initial budget, but at every step, the user budget reduces by the amount which is equal to the cost of the item. And then we also keep track of the list of items that the user has examined. So whatever user has examined, we append that to the list. So here I would like to pause for a second and recap what we have been able to accomplish. So we have been able to create a simplified version of the original problem. And what were the simplifications that we were able to do? So we used a very simplified state representation. Essentially, the entire state of the user is collapsed into just like one scalar, which is the budget. And the other one is the list of items examined. The state transition becomes really simple. It's a deterministic state transition. We just append the item examined into the list that the user examined and update the user budget. We have a simplified user reward model, just the Bernoulli reward, which is proportional to the relevance of the item. And then we have some intuition about what a good solution would look like. So essentially, like from the illustration that I had earlier, so a good solution essentially includes recommending relevant items, but also more of them, because we're now like thinking about the combined utility of the slate and not just of one item. So that said, we can now simulate different conditions and then evaluate results in a simulated on-policy fashion. So one of the benefits, again, working in this unit test like /simulation setting is that we have the user model. So we can generate different slates and pretend that the user will look at those slates, and then we generate rewards using the user reward model. So next, I'll talk about the experiments and some of the results. So I'll be talking about two metrics. One is the play rate, which is essentially what the agent is trying to optimize. So it's just trying to construct like slates which have higher play rate. So it's just the ratio of the successful to the total number of slates that the users see. And another metric, which is the effective slate size. So I actually skipped over the definition of effective slate size in this slide. I want to show it again. So effective slate size is basically like how many items the agent is able to fit within the user's budget. So obviously the effective slate size can be as large as the entire slate, but since I mentioned that only the items which fit within the user's budget, they are relevant for the user. So the effective slate size is basically just a subset of the total number of items in the slate. So effective slate size is not something that the agent is trying to optimize. So just tracking effective slate size gives us an idea about the mechanism of improvement, because one of the things that the agent can do is to construct bigger slates by putting like more items within the user budget and each of those items being relevant as well. So that could be one way to get better slates. And as I mentioned earlier, metrics are computed in an on-policy fashion. And for most of the results that I'll show, the metrics are relative to the contextual bandit, because contextual bandit is a simple approach, very popular in reinforcement in recommendation system research and application. And we will be using two RL models. One is going to be a vanilla on-policy optimal value function learning that is known as SARSA, and the other is going to be an off-policy method, Q-learning. Okay, let's look at the results. So the first set of results are going to be for the on-policy method, and we will be studying the effect of the user budget. So along the x-axis, I have the user budget. So the takeaway from this result is that when the user's budget is large, contextual bandit and reinforcement learning model perform similarly, because like the cost of the items, they are not relevant. So both of them would perform similarly as anyone would expect. But when the user's budget is small and the cost of the item becomes important, reinforcement learning starts to outperform the contextual bandit, because like that's where the trade-offs exist, and reinforcement learning agent is able to make better trade-offs compared to a contextual bandit. So we can also look at the effective slate size. And again, like all these results are relative to the contextual bandit. So we can see like the reason that the reinforcement learning agent is getting higher play rate compared to a contextual bandit is because it is constructing larger effective slate sizes, and the mechanism, and that's basically like one of the primary mechanisms that the RL is using to get better slates. So reinforcement learning is able to fit more items within the user budget. And again, it's intuitive because the RL model can plan for the future, and it can basically like only recommend items that it knows doesn't inhibit its ability to recommend more items in the slate to the user. Discount factor is also an interesting parameter. Mostly, so discount factor is necessary in continuing tasks because you need to define, because discount factor lesser than 1 is needed to ensure that the return is finite. But discount factor is important in episodic tasks as well because it basically controls the immediacy of reward. We may prefer a sooner reward. We may prefer a reward that comes sooner than later. And discount factor equal to 0 is purely a contextual bandit, which is the extreme case that we only care about the short term, like the most immediate reward. And as a function of discount factor, we don't see any difference between the contextual bandit, which is basically like the result at discount factor equal to 0. So there isn't any significant difference. So this result is for a fixed user budget. So the earlier result I presented was a sweep over the user budget. And we did see that for smaller user budget, reinforcement learning agent is able to outperform the contextual bandit. So this result is for a slightly larger user budget where where actually like reinforcement learning and contextual bandit, they perform similarly. And again, we can look at the effective slate size, although play rate was same as a function of discount factor, but the reinforcement learning agent was still trying to construct bigger slate sizes, was trying to construct like bigger effective slates. And again, like it's intuitive because the RL algorithm cares about the reward, the later reward as well. So as you increase the discount factor, it tries to construct bigger and bigger slates because it also cares about reward that comes later. So the last two results are comparing on policy versus off policy. This is a very interesting result because on policy, as I mentioned, it's very flexible, but it can be very expensive and probably like inconvenient for users to experience, and off policy gets around all those problems. So in this result, we compare the play rate that we obtain from the on policy method with the off policy method, specifically Q learning. And here, like, I mean, we're looking at the results again as a function of user budget, which is probably like one of the strongest parameters in this study. So the play rate is, so it was good to see that the play rate is very, very similar between the on policy method and the off policy method. Here, the metrics are relative to the on policy method. So as you can see, like the error bars, they hover around, they basically cross 0. So it was good to see that on policy and off policy method, they achieve similar resolution when it comes to the metric. Although like off policy method was doing similarly in terms of the play rate, but was still interesting to see that they were coming up with different solutions. So off policy method was creating larger effective slate sizes, especially for low user budget. So even in simulations with all the simplifications we have made, there could be some surprising results. And this is one of those surprising results that they were achieving similar play rate performance, but the solutions that they were constructing, specifically when we try to look at them from effective slate size lens, they were quite different. And so this is an interesting result. I don't fully understand it yet, but something to investigate more. So at this point, I would like to ask this question, that how do these results help us? So you may wonder that the real world is more complicated than this unit test task that we created for the slate construction, and it is true. But the point is that if we can't explain the behavior in such simple tasks, we may find it even difficult to, when the real world and the real data is involved, when you're using like the full feature representation for the state and you have a very large feature representation for the action as well. So it may be very difficult. And if the algorithm is not behaving as you would expect, how do you explain that? So it's much easy to explain these things in the simple setting. And that's basically like the whole benefit of thinking the problem from a unit test perspective. And the unit test style evaluation is essentially for intuition building and being able to understand the mechanism of improvement. And one example of that mechanism was the effective slate size that I was showing. More details about this work in the blog post. And then there is an accompanying notebook as well, where you can change the variables of the environment, change the model, and then do all kinds of studies if you have a problem which is similar to slate construction. So to conclude, as in all RL research, we found simulations very valuable for recommendation systems. I started with my story of applying RL in the real world slate construction task and mentioned all the challenges. So we get around all of those and we start to see like RL can have some benefits and upside, and that gives us confidence to move ahead with the full problem. And combining ideas from simulation, unit testing, and benchmark tasks, we were able to create a simplified version of the original recommendation task. And such unit test tasks can help us estimate the benefits and upside of a particular technique before solving the engineering challenges, which are plenty when you're thinking to apply RL in applied settings. So that's it. If there are any questions, I'm happy to take those.
Let's thank Adeshem again. We have a few questions from on the Zoom, and people can put them there. Once I can come up here, I can hand you the mic. This is a question near and dear to my heart. How easily does it extend to two-dimensional representation of a slate like page construction?
Yeah, so one easy way is that you consider the item as, so one like super easy way would be to again consider the page construction, which is 2D essentially, as again a one-dimensional problem where where the items are now rows, one-dimensional objects, and then you consider a stacking of them. So that would be one way to consider extending it to the two-dimensional page construction. The other, so that obviously would be the first step, but more comprehensive way would be to look at a Markov decision process again as a sequence of items, but now they are arranged in a grid, and then you can consider like some kind of a user browse pattern, and then that's the way like how the sequence would be arranged. So the MDP idea can still be applied on 2D grid, but then you have to decide like which way the grid is traversed, and that can be learned from user browse patterns.
Thanks, Asham, for the great talk. I have a question around exploration. Did you look at any exploration strategies paired with SARS, and did any of them make a difference in the results?
Yeah, so one piece I did not cover was the architecture of the slate construction recommender. So essentially, like all these methods which were learning the value function, they get passed to an epsilon greedy sampler, and then there is an epsilon greedy sampler which would do the exploration. And yes, so if there isn't any exploration, it's hard to learn the value function. So yeah, that part is like important. I didn't study like the effect of. I studied the effect of the exploration rate, but in another context, but not in this. Yeah.
Another question from the Zoom. What Q-learning flavor did you use?
So the Q-learning flavor, we experimented with both Monte Carlo style method because it was a finite episode. You can get the entire return for that episode and then regress against that. That should be the starting point for any one who is interested in applying a learning value function. But then we found temporal difference learning to do much better than Monte Carlo method. So all these results were based on using temporal difference learning instead of the Monte Carlo method.
How would you deal with a user state is modified due to external factors and not only by the interactions of the agent?
Yeah, I think that's a good question. So here, I hope, when the state is stochastic, we can capture some of those external factors. So, in this simulation, the state transitions were considered deterministic, but obviously real world is more complicated than that. And stochastic behavior is probably more suitable. So many of those external factors probably can be captured by considering the state transitions as stochastic. But if there are external factors which are very strong and they are affecting our ability to estimate the state transition, then that probably will make it difficult because we may find out that the effect of action on the user may be very weak, and most of the state transitions are actually happening because of external factor. And that actually probably is the case with the stock market example that I was showing earlier, that when the action is taken and the action is too weak, it's a small amount to invest in the market still changes its state, but not because of the action taken by the agent. So probably in that case, reinforcement learning would be hard to make it work.
I have a question. I wonder if you ever tried your actual policy online in an A/B testing fashion to test out if at least the direction-wise, the metric is aligned with the simulator. Because from a very intuitive sense that the simulation can only as good as the rewards that you constructed. And I used the user relevance score as the reward. So I was just wondering like how accurate this kind of simulator compared to the A/B testing.
Yeah, this was super simplified version, and that's why I called it as a unit test and not like a good representation of reality. There is work happening inside Netflix where we are trying to construct better simulators, and we can trust, and then we can basically think more about a gap between simulation and reality in more detail. So as for the A/B test, I can't talk much about like the details of A/B testing, but I mean, these are ideas that we're always interested in and in trying out. So yeah.
Cool. I think that's all the time we have for questions right now, but let's thank Edisham again. And I think he's going to be on the panel later. If people have more questions, and we'll be around also. So yeah, next up, we have Yoonwook Kang from Texas A&M University, talking about a contextual bandit problem with a bounded O1 regret policy. So let's give Yoonwook a round of applause again.
Hi, this is a joint work by my advisor, PR Kumar, and it's a theory work on how to apply contextual bandits for the RecSys. I'll make it as non-theory as possible so that practitioners can be entertaining. So I'll try to convey two ideas. First, about how the perspectives on RecSys for platforms and how bandits or RL inference idea, imputation detail, can actually innovate the RecSys. So when I talk about platforms, platform is a buzzword, but I say it's an intermediary in the two-sided markets where it connects buyers and sellers. Okay, so Apple Pay possesses iPhone sellers and connects them to card people. Amazon possesses Prime users and connects them to manufacturers. Netflix is a bit different story, but possesses subscribed users and connects them to movie distributors. Okay, and what happens is that they draw. Oh, there's an issue. It's not shared, right? Okay. Okay, I was saying nothing, so it'll be all right. Okay, so yeah. So what happens is that when platform gathers buyers and get the revenue from them, they share the revenue with the sellers. Okay, and how can I? Sorry, I'm not used to a Mac. Could you like make it a presentation? All right, that's simple. I think I can. Thank you. Okay, so I was talking about the sharing the revenue with the sellers, and then there's a quote by Susan Essey, a former chief economist at Microsoft and a Clark medalist, saying that a platform's market power for the larger share of the revenue actually doesn't come from data. It comes from platform's ability to aggregate the users and then control the users' access to that users. Okay, data only supports them. Okay, and when you think about the heterogeneous valued goods like music, movie, like that, the control over the seller's access, what's determining it is actually RecSys. So compare it to the previous type of platforms like for Uber like that, for the homogeneously valued goods. It's actually what does the job is a rating, right? So in this perspective, the new goal we can think of is making RecSys being much more than an average rating. Okay, so it can be like word of mouth or the websites ranking, providing rankings. Okay, so with that new goal, the fundamental bottleneck there's not like arrow showing. I was actually expressing the vicious cycle. So here in the fundamental bottleneck. So suppose that there is a item shown frequently, okay? And then it'll get a precise rating, and comparing to the items that are not shown frequently, they'll have ex ante less value in expectation, so they'll be shown less, and then they'll get less reviews. So then the item frequently shown will again frequently shown like that. There's a kind of like a vicious cycle. So partial answer to that is that contextual bandit techniques can actually break this feedback loop and remove such biases. So there's a report by Netflix last year. It's really interesting. I recommend you to read it. But actually in practice, contextual bandits suffer a lot in practice when there's a large action or large product space. Okay, so this paper investigates how the causal inference idea in detail, the imputation actually can address this challenge. So the result you'll see in the end is that the green graph means that there will be no cost regret accruing after a finite time step. That's result. How we achieve that? So let's first do it on the same page for everyone. Let's look into what the contextual bandit. So if you don't know contextual bandit, you can think of it as like a model, decision model, where there's a given context at every decision. You can think of it as an information you know about the environment, and you have a model in the mind about the reward associated to each actions. Okay, under the context. So after you observe a reward, then you update the model in your mind, and if you want to apply contextual bandit model for the RecSys, the assumption you're making is that you are embedding the entire user history into a context vector. It's like Amazon is purchase history, like watch history, listening history for Spotify, like that. Okay. So, but here's a challenge. So, if the user history accrues over time with a new experience, the user's context we generate changes, right? The typical approach to resolve this is that we don't care about who the user arrived, and only care about the what context vector is newly generated. And only the context reward history is recorded, and there's no keeping track of user reward history, okay? And this is useful, kind of conservative manner when the context dramatically changes as the history accrues. But is it really true for the platforms? Like, if the history is enough compared with the new experience, then the context won't really change for a short time, okay? And what it suggests is that if we fix individual users' context for a short run, and that will be justifiable if the exploration finishes really quickly. And then if we model each user's recurring arrival using maybe a stochastic process, and then we keep track of user reward history, then there will be something we can benefit from that setting, okay? So let's look into the concrete example of what I'm considering. So let's say we are looking into Spotify, and let's say there are like Kanye West-like musicians, like sub like genre, like Bieber-like musicians, and then like Nicki Minaj-like musicians. And let's say there's a green user just arrived, and we know the context or the vector of the users, and then each vector associated to each the musician-like genres, we don't know. And then the reward is calculated by the inner product of the user vector and the genre vector. So that setting, if you know about the linear contextual bandits, to justify it, our setting and the typical linear contextual bandit difference is an exact analog between the matrix factorization and the neural collaborative filtering. Last year, there was a paper about comparing these two and showing that matrix factorization actually can do better than neural collateral filtering. So that's a justification in terms of RecSys. So how the algorithm goes, like in a very high level, is as follows. So what we do is blue, red, purple person, we choose them as top 3 Bieber-like music users until now, okay? And then what you do is express the green user we're interested who just arrived as the context vector of that Bieber-like music users, okay? Because it's a 3-dimension vector, we can express it as a linear combination, and then we can generate the linear combination as a linear combination, the expected reward. And also what the technology I'm suggesting here in the paper is that we basically impute the uncertainty by imputing the UCB index of the user J for the Bieber. So note that user J actually have never expressed Bieber. He hates, maybe they hated, right? So, but we imputed the UCB by the Bieber-like users UCB. Okay, so if you don't know what UCB is, just think of it as the optimistic guess index. So that's UCB intuition. So how the algorithm goes is like this. So let's say AK is the user who arrived at the case arrival, okay? And for the all arms, what I do is at every arrival, we compute the UCB, which is its own optimistic guess. And then and also we compute imputed optimistic guess by counterfactual UCB. And then what you do is reducing its own guess by the imputed guess, okay? So, and then we use that index for the decision. You can like recommend user, like choose one and recommend like that. So that's the detailed algorithm. Oof, okay. Okay, so sorry that my PPT like a bit screwed up after conversion, but the theorem goes like this. I won't go to detail of the reading it, but what you can just think of it as is that if you have enough users compared to the number of sub-genres, then you're happy. So it's like okay, it's almost done. Okay. So let's say you have 10,000 sub-genres exist, and the number of users in a Spotify is like, and then the number of you need to actually guarantee 99% of the condition we need is actually 250,000 users. That's enough. So it's much smaller than actual users, right? So in that case, in that the condition holds, then what happens is that no user actually pulls on wrong arm at all, actually, after some finite arrivals. So the green is with the recommendation algorithm. The red is the with the no recommendation help. The graph is about the cost occurred. So you can say that there's no cost occurring after some finite time step. So the conclusion is as follows. What I showed is that we know, like, in the causal inference community, imputing missing values using the matching, the synthetic controls like that, right? And what I showed is that imputing missing uncertainty can actually innovate the contextual bandit for RecSys. So under following implicit conditions, that there's no noise in the data, information we already know, user vectors, and then the user vector has sufficient information for uncertainty imputation. So we can limit the effect of unobserved coverage, like we do in the synthetic controls by Abadi et al. Like paper. And the question is like, would the uncertainty imputation still work after relaxing such assumptions? It's a open question. So about the future like research, the uncertainty quantification is actually a really hot topic in the ML theory. So I suggest advancing it together toward the causality direction. That's what I'm saying. So that's it, and thank you very much.
Let's see. If you have any questions, just please raise your hand or come up here and I can hand you the mic. I had one question. Just it sounds like the way you have it set up might require knowing a lot about like what your example, like what type of artist someone was interested in ahead of time. So I'm just curious, how do you typically, if say use a cold start problem, right, is a very common case. Like how do you think this would work when someone's pretty new, maybe doesn't have a lot of items they've interacted with yet?
Oh, so you mean like we don't know the context actually?
Yeah,
right?
yeah. So like, what do you? How would you kind of think about using this type of approach in that case?
Yeah, that's a different story. The complete different research. I have actually working on that. Like, that becomes a multi-agent bandit problem with no context, right? So I'll make it like available like in 3 months, 2 months. Yeah,
Okay.
yeah.
So it's coming.
Yes, yeah. I hope it will be coming. Like,
Cool.
not very far from now. Okay.
Awesome. Any other questions? Any online? Otherwise, yeah, let's thank you again so much for your talk. Great. So next up, we have Ben London. The slides are coming up. Awesome. From Amazon. Thank you. And Ben is going to be talking about control variant diagnostics for detecting problems in log bandit feedback. So welcome, Ben.
Hey, so just going to take a sip of water. When you present the nice things that you get to drink water, you in the audience don't get to drink water. Okay, so thank you all for attending this. I realize that I am standing in between you and your lunch, so I'm going to try to be as brief and engaging as possible. Today, I'm going to be presenting joint work with Torsten on detecting problems in logged bandit feedback, which is the type of data that you might collect for a recommender system, which is, why we're all here. And hopefully I can convince you that this problem is important, and I'll present some ideas that we have for ways to solve it. So let me just make sure, oh, let's move this. Is it possible to move the Zoom bar out of the way? Sorry.
Let's see the mouse.
Yeah, it's really. Oh, great. Awesome. Thank you so much. Okay, yeah, so we all know that recommender systems generate a ton of data, and one way to characterize this data is as bandit feedback. Now, what I mean by this is that we show you something and we observe your feedback for that thing that we showed you, but we don't get feedback for the things that we don't show you, or like the things that you just don't see for whatever reason. And the reason that we care about this data is because we can use it to evaluate and to optimize new recommenders. And in the bandits and reinforcement learning literature, this is usually called off-policy evaluation and learning. And typically we do this offline because we don't want to harm the user's experience. Now, off-policy evaluation is a challenging problem because it poses a counterfactual problem of figuring out what would have happened had we done something different from what we actually did. I'm not really going to touch on that problem. There are many methods to deal with this, but I'm going to be focusing on the data that we use for this. And the question that I want to answer is, given a data set, is this data good? Now, there are many ways to define what good means, but today I'm going to say that data is good if it allows us to estimate in an unbiased way the expected utility or the expected reward of a new policy. And this is, critical if we want to find out how a policy is going to perform before we, deploy it and have it recommend things to users. So there are a few ways, well, a few families of ways to estimate reward. And I'm going to be focusing on the family of importance-weighted estimators, the inverse propensity scoring estimator, which I'm showing here. This is just the vanilla version. There are many variations on this, but let's just consider the standard one. This is essentially just a weighted average of the observed rewards, where the weights come from the ratio of the target policy, pi, the probability that it puts on an action, divided by the logged propensity that the logging policy put on that action. And as many of you are probably already aware, this estimator is unbiased when the following conditions are met. So first of all, we have to have a logging policy that is sufficiently randomized, by which I mean in any given context, any action that is available to a future target policy has to have non-zero probability of being observed. And we typically call this the full support assumption. Now, the second requirement, which may seem kind of obvious to everyone, is that the data has to be logged accurately. Like, we need to know the actual values. And in particular, we care about the propensities, and that's what I'm going to focus on today. Yep, slide's not advancing. 1 second. Okay, great. Yeah, got it. All right, so when can things go wrong? So one pretty straightforward case is when the logging policy just isn't random enough. Usually your logging policy will be some learned parametric model. Maybe it's like a softmax policy. And if you don't have guardrails in place to ensure a minimum amount of randomization, then you could end up with some contexts where there are some actions that don't have any chance of being selected. And it's important to note here that I am assuming that when we log the data, we only log the propensity of the action that was shown to the user. We don't log the full action distribution, so you can't just like look at the logs and say, oh, are there any zeros in the propensities here? And I would argue that this is kind of a, in some cases, this is pretty realistic. Another way that things can go wrong is when the propensities that you've logged don't accurately represent the probability of observing an action. So for instance, a recommender system, or rather the policy that selects the actions is typically part of a larger recommender system where after the policy selects things, there are some filters or some guardrails in place that prevent, crazy recommendations. That influences the distribution of observed actions in ways that might not be reflected in the logs. Another thing that could go wrong is that there are just like systemic failures where, the system is like filtering out certain actions just because they're, because of latency issues or something. These are real issues, I might add, in my experience. Which brings me, brings me to my next point, which is that these issues happen all the time, and it seems to me, just based on the literature, that no one is really talking about this, and so that's what's motivating this work. There's one other paper that I'm aware of that mentions this, a paper by Li-Hong Li, and they kind of briefly discuss these issues, and actually they propose a diagnostic that's kind of similar to the one that I'm going to show you next. But yeah, other than that, I'm not aware of anything. So, please come to me after the talk and let me know if you're aware of other work. Okay, so what we propose are some simple diagnostics based on the idea of control variates. A control variate is just a statistic with a known expectation. And typically it's used in Monte Carlo methods to reduce the variance of an estimator. So for example, in offline bandits and reinforcement learning, you might have seen a control variate of this form, which is just the average of the importance weights. And this is used in the self-normalized IPS estimator to reduce variance of the estimator. Now, a very convenient fact of this control variate is that when the conditions for unbiased evaluation are met, this control variate has expectation equal to exactly 1 for any target policy that you can pick. And So we can use this to develop diagnostics where we, given a data set and a specific target policy, which I'll get to in a second. So given a target policy and a data set, you compute the control variate, and we expect it to be around 1. But if it differs significantly from 1, then we say, aha, something might be up. Now, I'm just focusing on like detecting the issue, what you do once you've detected the issue, how you debug it. Like that's a whole can of worms, which I'm not going to get to. But my goal is to be able to just say there is an issue with this data set. And you can kind of view this as a hypothesis test where the null hypothesis is that the data is drawn from a good distribution. But if we observe a control variate that makes us reject the null hypothesis, then we can conclude that maybe it's drawn from a bad data distribution. And so it's important to note here that the diagnostic does depend on the target policy that you choose for the control variate. And certain target policies are better than others at dealing with certain types of problems. And so in this work, we are just introducing 2 simple diagnostics based on a couple different target policies. Okay, so the first diagnostic is what we call the uniform diagnostic. This uses a target policy that selects actions uniformly at random. And so what we do is we compute the control variate for the uniform policy. And then if we compute a confidence interval for this control variate, and if the confidence interval contains 1, then we say everything's okay. But if it doesn't contain 1, then we say something's up. The second diagnostic is based on a target policy that always picks the same action. And that's why we call this the always pick A, or the APA diagnostic. So for each available action, we compute a confidence interval for the control variate based on the policy that always picks that action. And then if any of the confidence intervals do not contain 1, then we raise a red flag and we say something's up. And that's cut off. But basically what that's saying is that we call these the practical diagnostics because they don't require us to set any threshold parameters, and they're just based on simple confidence interval methods. But when I get to the theory in a couple slides, I'm going to slightly change these diagnostics so that they can, so that we can improve things about them. Okay, so now that I've hopefully convinced you that control variates are awesome and they're so useful for detecting these types of problems, I'm going to tell you how they're not so great. So control variates can detect some problems, but they can't detect every problem, or there's no test that I know of that can detect every problem. And so having good data is a sufficient condition for the expected control variate equaling 1, but it is not a necessary condition. And so there are some problems for which you could have an expected control variate that equals 1, but there's still an underlying data problem. And so in that case, we just can't detect that problem with these types of diagnostics. And we show this in the paper. Another issue is that we're dealing with a finite data sample. And so if we don't have enough data, we might not get a meaningful confidence interval. And that could lead to a false negative. Or if we pick the wrong target policy, it could overemphasize certain importance weights, and that could lead to a false positive. So, we can't detect all types of data problems, but what we show in the paper is that we can detect a couple of these provably, right? That's what we want to show, is that we can provably detect certain issues. And, it's going to depend on the diagnostic and the target policy. And so I'm just going to show you a few cases, or 2 cases right here. Okay. So the first issue that we can provably detect is when the logging policy is support deficient. Again, this just means that in certain contexts, the target policy didn't put non-zero probability on all available actions. And if we assume that the expected support set is upper bounded by some value that's less than the full support size, sorry, the action set size, then the expected control variate will be strictly less than 1. And in the paper, we give the actual expression for the upper bound, but the important thing is that it's strictly less than 1. And this is for the uniform target policy. So this motivated the uniform diagnostic. The second type of issue that we can sometimes detect is when we have logged the propensities incorrectly. Now, in general, it's hard to find a diagnostic that will always work for detecting incorrect propensities. And in the paper, we give a construction that shows how sometimes you could have the wrong propensities, but your expected control variate is still going to be equal to 1, and so you just can't detect this. But for a very, I would say, realistic issue, we can detect this problem. So when the logging policy is part of this larger system that has some post-processing, some filtering, if there are certain actions that are like just not available in certain contexts, but the logging policy doesn't know about this, that could bias the propensities that it's logging. But it just like isn't aware, right? So this is kind of like being support deficient because there are certain actions that are just not possible to observe, but the logging policy doesn't understand this. And so it's just, selecting those actions and logging propensities as if those actions were available. And whoa, that looks funky. All right, well, if we assume that there's a good set of actions that are always available and a bad set that are sometimes not available, then for the target policy that always selects a given action, its expected control variate is going to be either greater than or less than 1, depending on whether it's in the good set or the bad set. Okay, so these are just 2 results for bounds on the expected control variate. We can use these bounds to prove bounds on the false negative and false positive rates of the diagnostics that I mentioned earlier, with some slight modifications where we have to specify a tolerance parameter for the theory, and also just make an assumption about the minimum propensity for the actions that are in the support set, right? So we can still have some actions that have 0 probability, but for the actions that have non-zero probability, they have to have their probability has to be lower bounded, or we need to just have that constant. Anyway, I'm not going to get into the theory because we just don't have time. But the main takeaway from these bounds is that the false positive and negative rates decrease exponentially fast with the size of the data. And for the APA diagnostic, since it's designed to be a bit more sensitive, it trades off precision for sensitivity. It is actually the false positive rate is sensitive to the number of actions. So we ran some experiments with synthetic data just to see if these diagnostics actually work and to validate the theory. We used a non-contextual logging policy, which just means that the features are irrelevant here. Also, rewards are irrelevant because we're not actually using the rewards. All we care about are the actions that are selected and their propensities, which in this case, the propensities are just inversely proportional to the actions index in the action set. And so the first thing that we wanted to see, again, sorry about the equations. The first thing that we wanted to see is how these diagnostics behave when there is no underlying issue. So in other words, what is the false positive rate? And so we generated data from a good distribution and measured how many times the diagnostics triggered incorrectly. And what we find is that the false positive rate of the uniform test is pretty constant while varying the number of actions. But for the APA diagnostic, as expected, it is sensitive to the number of actions. We also tried varying the number of records, and again, according to the theory, the false positive rate should decrease, and it did. For the APA diagnostic, it was slightly higher just because, again, it's tuned for sensitivity. Okay, so we also tried the false negative, or sorry, we evaluated the false negative rates. And so to do this, we had to construct data issues with this synthetic data generator. So the first thing that we did is to simulate insufficient support. And so what we did is we just would occasionally make the logging policy put 0 probability on just one of the available actions. So in this case, there are 10 available actions. And with some probability, the logging policy is just setting the probability of one of those actions to 0. And so here I'm plotting the expected support size. And this has a maximum value of 10. So one thing to note here is that the x-axis is like, the range of values I'm showing here is very close to 10. Basically what these results tell us is that the expected support has to get pretty close to full support in order for these diagnostics to miss the underlying data issue. They are pretty sensitive to the data issue. As expected, the APA diagnostic is slightly more sensitive. We also simulated the second data issue where, then this is meant to simulate incorrectly logged propensities, but in the scenario where the logging policy just isn't aware that certain actions will be filtered out later. So again, the x-axis is expected support because that's basically the parameter that we have to tune here. It's important to note that the uniform diagnostic is not guaranteed to work in this case, but we find that it actually works pretty well. But the APA diagnostic, which is designed to work for this case, is working even better. Okay, so in summary, if you take away nothing else from this talk, please just take away the idea that these types of issues are common. Hopefully you agree with me on that. If you work in industry, you probably do. But they've received not much attention in the literature. And so hopefully, we can get people to start thinking about them and, thinking about creative ways to address them. We have proposed just a couple diagnostics based on control variates, and these seem to work in the cases that we have identified, but there are other cases which we would like to be able to catch. Ideally, we wouldn't have to come up with a bespoke diagnostic for each type of data issue. Hopefully, there would be like more general conditions that we could identify that would, detect all sorts of data issues. And ideally, they would, be both sufficient and necessary conditions. And then lastly, we would like diagnostics that just go beyond just simply saying, yes, there is an issue, to diagnostics that say, yes, there is an issue and it's probably because of X, Y, Z, right? We want to be able to debug these issues, not just detect them. All right, that's it. Thanks.
Thanks again for the great talk. And I do vouch for that. These are very real issues. So it's great to see some work to try to make it so you can find them a little easier. We got a few questions online. How would this method work when there's a number of actions is very, very large?
Yeah, so so the theory is assuming that the action set is fixed. This is maybe not absolutely necessary. It just, makes the notation a lot simpler. I would say for diagnostics like the always pick a diagnostic, that would probably become infeasible. But the uniform diagnostic should not be affected. And, in terms of the theory, it shouldn't be sensitive to the size of the action set.
So next question. Sometimes you have data sets with no log propensities. You have to estimate them for each data point. Can you use the diagnostic to understand the quality of the estimation?
Yeah, that's a great idea that I've kind of been thinking about, right? Can we use this diagnostic to say that the estimated propensities are, reasonable, or rather, will the estimated propensities give us an unbiased estimate of reward? I think that's a great idea. It's not something that we've looked into yet, but I think it, we could.
Next question. Can you use this to look for a covariate shift or only to evaluate the data quality? So,
well, I mean, covariate shift, it would have to be some sort of covariate shift in the in the logging policy. I don't know, maybe I haven't completely understood that, but yeah, I'm not sure it would detect general covariate shift. It's mainly just about seeing if the propensities match the distribution of actions that we've seen. Not the, if you're talking about covariate shift in the features, that's slightly different. Yeah.
Okay, here's the last question. It's a spicy one. To what extent do data issues invalidate the utility of IPS estimators? Can we still use them when the data issues are limited?
Well, I guess if you don't want to use IPS, what you would use like direct method, and then yeah, I guess maybe you don't really care about the propensities. Sure, I'm willing to entertain that thought.
Cool, awesome. Well, thanks everybody. Thanks again for the great talk. Now we have up next, we have a lunch break for an hour, and so it's a quick, eat quick, run, get your food, come back, because we're going to start at 1:40 with the next invited talk. So look forward to seeing everybody then.
RL, which is a platform for offline reinforcement learning and policy evaluation designed from a practical perspective. Okay, so please join me in welcoming Haruka.
Hi, I'm Haruka Kiyohara, an undergraduate student from Tokyo Institute of Technology. Today, I'm excited to share our work, OFRL, designing an offline reinforcement learning and policy evaluation platform from practical perspectives. So reinforcement learning formulation is gaining a growing interest as it can model sequential interactions in recommender systems. For example, it can model sequential interactions in search as in slide. And we can also model sequential interactions in conversational recommendation and also the music streaming system. And now, to maximize some long-term metrics, such as lifetime value or the sales in the long run, we are interested in optimizing the decision-making policy to deploy to the online system. However, a potential concern here is that online learning and evaluation can sometimes be risky and costly because the poor policy can damage sales or user satisfaction, and the frequent update of the policy can easily incur huge implementation cost. So thus, to deal with those limitations of online learning, offline reinforcement learning is gaining a growing attention as a safe and cost-effective alternative for online learning and evaluation. And today, I'm gonna present a new offline RL platform implementation to facilitate the practical application of offline RL by especially focusing on the currently underexplored policy evaluation part. Right, so let me start from the motivation of our work, and let me discuss why we need a new offline RL platform in the presence of several existing platforms. Now, to facilitate the practical application of offline RL, it is very important to provide a whole streamlined end-to-end implementation of offline RL from the data collection to policy learning phase, policy evaluation phase, and also the evaluation of policy evaluation method. So first, providing our data collection module is important to extend the application area to the currently underexplored setting, such as online advertisement bidding or conversational recommendation. And then offline RL module is of course very important to enable safe policy learning using only offline log data. And after learning a new policy, because offline RL method sometimes works well on some narrow set of hyperparameters, it is also very important to verify whether the learned policy works well, again using offline data without directly interacting with actual users or before actually deploying it to the online system. And for this purpose of policy evaluation and selection is very beneficial, as OPE enables us to evaluate the performance of a counterfactual policy using only offline log data. And when we have several candidate policies, we can also select the best performing policy based on the OP result to reduce the risk and cost of deploying potentially, poor many policies to the online system. So we can say that this authority variation and selection is really beneficial to ensure safe and cost-effective policy deployment in practical situations. And finally, in addition to those three procedures, I'd like to emphasize here that providing an evaluation protocol or evaluation process of OP estimator is also, critical to facilitate the practical decision-making, because if we cannot, ensure the reliability of an OP estimator, then we cannot confidently conduct authority evaluation, nor choose which policy to deploy to the online system. So therefore, it is very important that we can first ensure the reliability of an OP estimator in a range of environmental settings. And for this purpose, it is very important to provide a whole streamlined implementation of offline area and OPE from the data collection to the evaluation of OP estimators. However, it is quite unfortunate that existing platforms and benchmark suits are alone insufficient to enable this end-to-end implementation of offline R and OP. So first, we have very nice, offline R library, which implements various offline R methods. However, those libraries often provide only limited implementation of OP estimators and also completely lacks the evaluation protocol of OP estimators. Therefore, even if we can learn various policies using offline R method, it is very difficult to identify which policy to deploy in the online system to ensure safe, practical decision-making. In contrast, we also have several benchmark suits for authority evaluation, which implements various of OP estimators and also the evaluation protocol of OP estimators. However, those benchmark suits are not flexible in their data collection and offline R module, and thus cannot enable an end-to-end implementation of offline R and OPE. And we also cannot, conduct the evaluation of OP estimator in a range of environmental settings, such as large action spaces of recommender system. And now, I'd like to also mention about Open Bandit pipeline, which was presented in the Reveal 2020 workshop. So maybe you are familiar with this Open Bandit pipeline. And I'd say this Open Bandit pipeline is a very nice platform that enables all of these four procedures from the data collection to the evaluation of OP estimators. However, this Open Bandit pipeline focuses on the contextual bandit setting, and thus is not applicable to the reinforcement learning setting. And finally, there are also some other application-specific platforms as well. However, those platforms implement only limited implementation of OP estimators, and also their application area is, of course, very specific. And now, summarizing those existing platforms, we now see that we are completely lacking a flexible end-to-end implementation of offline RL that enables all of these four procedures. Moreover, among these four procedures, we see that authority variation part is relatively underexplored, and we don't have so much various OP estimators implemented for practical usages. Therefore, it is very important to provide both an end-to-end implementation of offline RL and OPE, and also the well-organized, well-supported implementation of authority evaluation modules. And now, motivated by those missing parts of the existing implementation, we developed a new offline RL platform called OFRL. And the key point of OFRL is that OFRL is the first platform that enables an end-to-end implementation of offline RL. And compared to the existing method, existing platform mainly focusing on the policy learning part, we rather put focus on the authority evaluation part to ensure safe policy deployment in practical situations. Especially compared to the other existing platform, including the benchmark suits for authority evaluation, only implements basic OP procedure that try to estimate the expected performance of the evaluation policy. We are sometimes more interested in some risk functions, such as conditional value at risk, to further ensure safety in the practical decision-making. And motivated by this, we provide cutting-edge cumulative distribution of the estimator as well, which enable us to estimate the performance distribution of the evaluation policy. And using that performance distribution estimate, we can also derive various risk functions such as conditional value at risk or variance, which is indeed beneficial for practical decision-making from safety perspectives. And now, I'd like to demonstrate how our proposed OFRL platform enables an easy-to-use end-to-end implementation of offline RL and OPE, and also show how our implemented cumulative distribution OPE provides more fine-graded insight about the policy performance. So let's start from the data collection phase, and we can complete this in only 6 lines of code. So first, we define an RL environment, which can be an arbitrary environment in OpenEdge interface. So we can literally apply this OFRL platform to any environmental setting. And then we are learning a behavior policy using D3RFI library. And then we pass over this environment and behavior policy to the dataset class, and it's all done. It's very simple, and we can now collect the log data. And we can also skip this procedure if we use real-world dataset. And once we obtain the log data, it is time to learn a new policy offline RL. And here, we use D3RFI library that implements various state-of-the-art offline RL algorithms. And the point is that our OFRL platform is highly compatible to D3RFI. Thus, we can now leverage various state-of-the-art offline RL methods as well. And after running a new policy, it is time to evaluate their performance offline using OPS measures. And this is our main focus of OFRL platform. And here, we are converting the D3RFI policy to the evaluation policy. And we create some input dictionary and also initialize OP class using log data and OPS measures. And now it's complete. Again, it's very simple, and we can now get the result and also visualize the result. And here is the example output of comparing policy performance of various candidate policy using several OPS measures at the same time. And it is very easy to compare both candidate policy and also their OPS measures. And now, we can also conduct cumulative distribution OPE in a very similar manner to the basic OPE. And here we can now estimate the cumulative distribution function of the policy performance. And also based on the CDF estimate, we can also derive various risk functions such as conditional value at risk. And we can also estimate and visualize the interquartile range of their policy performance. So I'd say this cumulative distribution OPE really provides more fine-graded insight on the policy performance other than the expected reward, which is indeed beneficial in practical decision-making from safety perspectives. And finally, we're gonna select the best performing policy based on the OP result, of policy selection. And also we're gonna evaluate the performance of OP method and of policy selection method. And here, we are comparing the true and estimated policy metric. And it is clear that some estimators tend to underestimate the policy performance. So it is very easy to understand the behavior of the OP estimators in a very interpretable manner. And we can also evaluate the quality of policy selection using rank correlation or regret metric. And also we can validate whether the safety is ensured using type 1 and type 2 errors as well. And seeing those demonstrations, we can now find that OFRL platform really enables a very easy to use flexible implementation of offline RL and OBE, from the data collection to offline RL and OBE, and even to the evaluation of OPS measures. All right, so let me wrap up this presentation now. Today, I talked about potential application of offline RL and OBE, which can be a safe and cost-effective substitute for online learning and evaluation. And then, to facilitate their practical application, we developed OFRL platform, which is the first end-to-end platform for offline RL and OBE. And OFRL also provides very valuable, informative, fine-graded insight on the policy performance using cumulative distribution OBE. And as we see in the quick demo, OFRL enables very easy to use, quick and flexible prototyping of offline RL and OBE. And we hope this OFRL platform will facilitate the practical application, especially in the currently underexplored settings. Thank you for listening.
Thank you, Haruka. Any questions from the crowd? We'll probably take one question here and maybe one question from Zoom. Anything on Zoom? Nope. Okay, all right, thank you so much. So next we'll invite Bram Vandennecker from booking.com. He will be talking about extending open bandit pipeline to simulate industry challenges. And so there will be a little bit of prep here while the Zoom and the slideshow gets set up.
It's actually good because I want to take a selfie with the crowd.
Okay.
So everybody could stand up to get the blood flowing a little bit. Yeah. Go, go, go. Perfect. Mom's gonna love this. Everybody ready? Stretch it, stretch it. Oh, get everybody in. I'm in for sure. Awesome. Ready? I had a Star Wars joke, but I think that was a little bit too long, so I just wore the shirt. Let's get started. So to continue on the topic of open bandit pipelines, which was just mentioned, I'm presenting here our work on extending open bandit pipeline to stimulate industry challenges. And this was an amazing collaboration between these four beautiful folk. Nicholas sitting there in the back, and Felipe should also be in the crowd somewhere. So at the poster session, please drop by and we can have a chat. And Dima's probably sleeping. So to give you a little bit of a rundown of what we're going to discuss, just to have you know the key takeaways that you're going to get during this talk, we mostly describe five broader topic of challenges that we experience while implementing bandits in the industry. And it wouldn't be fun enough if we just presented those challenges. So we implemented 3 of these challenges to stimulate future work and also to give you a little bit more insights in what these challenges entail and how to work with them. And as mentioned, they are implemented in Open Bandit Pipeline. It's an incredible package of software, mostly for off-policy evaluation and learning, but we extended it to also do simulation, so you can do on-policy as well, and this nicely ties them together, so you can do both at the same time. All the code is available. It should be merged soon. And the setup will be sort of a lightning round, because I have very little time and many challenges. So I'll go quickly through all of them. Is everything going right? I'm not visible. I'm too tall of a Dutch person. That's probably the issue. And every round will be one of the challenges to be described. So first one, it has already been mentioned. I had in mind who mentioned it, but now I forgot. But on versus off policy is a major challenge for us. So somehow at Booking, almost all of our bandit settings are being solved with on policy, so really second update model changes. And this gives a lot of problems. And we want to understand when should we go for on policy and when for off policy, and how do you make this trade-off? It's actually not described very often in literature, if at all. So we would pose a couple of questions, and one that is mostly interesting: in which scenarios does off policy outperform on policy learning or on policy methods? And this is basically the first simulation that we created. So what we did is there's already synthetic data in Open Bandit pipeline, but instead of having synthetic data, and you probably cannot see this first call, but it's not too important, we have a Bandit environment simulator that we set up, where we can say how many actions are there, the context, and a bunch of other things describing the environment. And then what we can do is we can take the Bandit policy simulator, which you could see as your serving platform, inject a policy. These are very simple classes that you can extend to implement any policy you want, and then run this for a bunch of steps. Now, the nice thing is that this class contains all of your log data. So it becomes sort of your database, so to speak. And then you can go into the Open Bandit pipeline library of tools and just start implementing an IPW learner, for example, and then fit your IPW learner on all these different things that are stored into your in your logging policy. And then, check how off policy compares to on policy in that regard. Predict, obviously. So we added a couple of example simulations to show some of the questions that we're answering, or we want to answer, actually. And this very simple example is where we show, depending on the amount of rounds that you play your policy, you can play, for example, random, which is the eGreedy 1.0 at the bottom, or a bunch of on-policy methods, the three in the middle, and then the IPW learner that is vastly outperforming the Bandit setting. And this might be just the way we set things up, but we see this all the time. When you play with an on-policy method, you tend to have to wait a long time to get results. You cannot do hyperparameter tuning. You cannot control it very well. So with an IPW learner, it's much easier to get good results. And this is what we see here too. We also in the paper have some other setups where we, for example, check how exploration traffic affects how you can learn, which can also be interesting for many of you. The second major industry challenge, so we're now moving past the lightning rounds, it's not that fast yet, but we'll speed things up, is concept drift or non-stationarity. And everyone that has read a Bandit paper has probably seen that the environment is usually assumed to be non-stationary, stationary actually. And this is something we experience too, but we don't always know like what's the effect of this non-stationarity. And it's funny because the Spotify presented something earlier about adaptiveness and bandits and reinforcement learning. That's a common confusion that people get when they read these papers, that this adaptivity is not about concept drift. And then the product manager says, well, we just put an online bandit model there and we can move over all this concept drift and we'll be fine. But that's actually not true. So we posed the question, how many rounds does it take for an on-policy method to recover from different types of drift? And what we did here is we implemented something called a coefficients drifter. So the simulator works by having a context that is sampled, then we multiply with some coefficients and we do some magic there, and then we end up with expected rewards, which we can sample from. And the coefficients drifter changes these coefficients over time. And you can configure it with all kinds of different settings, like the drift interval, how often should it shift? How long should the transition period be between shifts? And also what type of shift? Should it be linear or should we do weighted samples? So go back and forth between the two different coefficients. Is it seasonal? Does it go back and forth between two different coefficients? Or does it just shift to new coefficients all the time? And how much is the base? So how much is consistent over time? And with this, we can run this, we just inject it into the simulator and the environment will start drifting. And what we can see here, and this, I love this graph because it shows exactly what all these product managers are confused about. The brownish line at top is just a stationary environment with an on-policy bandit. The other are different kinds of bandits on a non-stationary seasonal environment. And the first couple rounds, you see that they are performing about the same. And as soon as the drift hits, you're missing out on your performance. You're getting a bit hit. But even when you then shift back into the season where you started in, you're still having that hidden performance, and these bandits cannot adjust. And intuitively, this makes it super easy, and anyone that works with it a lot will know this, but it's hard to show this and hard to reason about. The third topic is delayed rewards. And this was also briefly mentioned a couple of times about like things coming in later. And the big question is like, what extra regret do you get when the environment, when you have delayed rewards, both in stationary and non-stationary environments? In a classical bandit setting, rewards come in right after your prediction. But this is not always true, was actually never true in a production environment. So what we did is we introduced something called a exponential delay sampler, because so far all of the delays that we've seen were exponential, where you can simply say we have an exponential function, and every time we make a prediction, we take an X amount of round sample from this exponential function to receive the reward. And we can do this either just by an exponential function, everything is unbiased in that sense, or we can do this based on the reward. So the expected reward influences the delay. Now we can inject this in the environment again. And what we can now see is here, this is one of the examples where you see that if we have this exponential delay in a stationary environment, we might incur a lot of costs at the beginning. But because we do more exploration, that's at least our assumption, because we do more exploration at the beginning, we still recover to a similar value over time when we take enough time, because we still get the rewards at some point, or the feedback at some point. But when we combine this with the non-stationary environment, we see that there's actually a gap. So here we see that there's actually a gap being introduced. The green line is when there's no drift, and there's a delay. The blue line is where there is no delay and there's drift. And then the orange line is the drift and delay. And you see that there's a difference between those two. So delay can actually have an influence on your actual reward, especially when your environment is non-stationary. So we had 3 different problems that we built simulations for, and then we ran out of time. Luckily, I have time at this talk, so I can go to the last 2 in concept. And this one, the business rules, is actually something that was mentioned by Amazon, by Ben, in one of the previous talks. And it's something that we constantly experience. So in a classical bandit setting, you always can let the policy decide what actions to take. However, in practice, there's always some sort of governance or some rules on top of it that might block actions from actually being shown. And what happens is we wonder, like, how is the performance of the bandit model affected when sampled arms are blocked by the system? This is hard to measure in practice because they need to be blocked anyway, so you cannot let them go in. But we've seen that when we do off-policy evaluation, for example, arms that are blocked, for example, when you give discounts to certain types of users, but you don't know at the time when you ask the bandit if you can give that discount, those discounts are probably going to give a lot of uplift in your reward. However, when you do off-policy evaluation, it will lift it up, but then in practice, you cannot give that action. So the whole model is going to make wrong decisions in that regard. And also, when you try to calculate propensities afterwards, this might be very difficult. This might break a lot of assumptions that you have. And finally, we call this reward design, is that this was mentioned before a couple of times as well, is that most bandit algorithms will optimize on clicks. That's what their reward is. However, we are usually interested in things like conversion that come way later in the funnel, or as mentioned by Spotify in the keynote, is we want to know if they are still interested in 4 months later, or they're still engaged 4 months later. And it's very difficult to incorporate this into your bandit setting, to combine these rewards. And we haven't seen, we couldn't find any research on this that really explains this, but I see some hands going up that this was just mentioned, that there was one paper that we couldn't find. But there's not a lot of public work that shows how to combine these rewards effectively for your bandit setting. So these were the 5 challenges, some of the simulation. We hope that you can check out the code, you can use it. There are notebooks that show how we got these results and how you can reproduce them and play with it. And we have this big poster in the hall. So if you want to chat, learn more about what we do, or tell us some things we've missed, love to hear about it. And that's it.
Okay, thank you, Brand. for this great talk. So questions now.
Hello, thank you for your talk. I have a question on the concept drift problem. How do you think, or do you think at all about endogenous concept drift?
Sorry, what type of concept drift?
Endogenous. So to this,
Endogen-
so the concept drifts because you sort of
Yeah, so
you know,
the feedback loop basically
exactly
that
because
happens.
you, like pull that arm.
Yeah, it's not something that was in these types of simulations, and it's also a lot harder, I guess, to do. But I would expect that if this kind of concept drift affects your performance, then those would definitely have a very similar effect. But it's definitely an interesting venture to go into as well.
Any other questions from the crowd? Okay, so we'll take some online questions now. So one question is, do you think that algorithms such as the doubly adaptive Thompson sampling, which Maria introduced earlier, could help close the gaps that you see between the off-policy and on-policy algorithms?
That's a very good question. I would have to read up a little bit more before I can really good answer the question, but maybe you want to answer the question. Jump.
Yeah, so precisely, you mentioned the concept about covariate drift. It's a similar thing. There is a large body of literature dealing with that. Some of that has to do with doubly adaptive Thompson sampling. So yes, to the person who posed the question, that is a method to approach that, but there are other approaches beyond that, importance sampling, weighted training, doubly robust estimation. So there is related literature. Same thing for the multiple rewards. There is a large body of literature on surrogacy assumption that's mostly related to what Dan just presented. So it's very interesting to have actually an environment that simulates this type of real issues. But for many of the challenges you mentioned, there is already a very large body of literature addressing this.
And we should definitely talk.
Sounds good.
Okay, I think that'll be it. Please join me in thanking Graham for this talk. All right, and now for the final speaker for this session, we have Joao Vinagre talking about skip-aware rec. And this is a sequential and interactive music recommendation system.
Okay, thank you. Hi, everyone. My name is João Vinagre. This work was done mostly by Rui. He's a master's student. Actually, he already finished. And this was work from his master's thesis. He was able to do a lot. He did like 90% of the work, or 98% of the work, to be more accurate. So the idea here was to use negative feedback from a data set to adjust the recommendations online. So basically, in a music listening session, you hit the skip button and you want the model to realize that and to reflect that. We use the Spotify's skip prediction challenge dataset, which is a dataset that contains music listening sessions with skips. And it also contains information about the music tracks themselves. So we studied a little bit of the state of the art, and what I figured is that there's not a lot of reinforcement learning for this type of task. There are a few contributions, but we didn't find any contribution that could actually use negative feedback such as skips, at least in the music domain. So we set out to do this using this data set. So it contains anonymized music track features. So we don't know the names of the tracks. We only have a set of features for each track. And it contains music listening sessions containing user feedback and other associated variables. So it has 1 million entries, almost 60,000 sessions, and 174,000 music tracks. So our first problem was basically our initial intention would be to use reinforcement learning and mapping items to actions. The problem is that the action space in music recommendation could be huge, and we quickly came to the conclusion that we couldn't do that, at least in the time that we had available. So we basically clustered the items into 23 clusters, I think, and we simply use the clusters as actions. So the problem is completely simplified like this. The problem is that now we cannot, as you might imagine, it's not very interesting to recommend categories, right? We need to recommend actual items. So what we did was basically use a simple matrix factorization algorithm. That is this ISGD here. It's an incremental algorithm that is very simple. And what we did is that when the reinforcement learning agent recommends a category, use that category to narrow down the candidate items to the ones belonging to it. And feed that and then use the matrix factorization algorithm to recommend items from that category, simply. So we map states and actions. We model states and actions using the categories. So each action corresponds to a category, and the states are the set of k most recent categories that the user has interacted with. So the reward function, for the reward function, we use the skips, and the data set contains 4 types of skips, according to the moment where the skip was done. From 1 to 4, the skip was done very early, late, and very late. And we also had to take into account something else, is that skips can be done in personal playlists. That are playlists that are curated by the user, him or herself. And skips have different meanings if the user makes a skip in such a playlist, or a playlist that is, for instance, recommended or curated by other users, etc. So we have a different reward value for each case. We use simple queue learning, so we didn't use anything fancy, so just a simple queue table. Our action space is very small. Yeah. Okay, sorry, I was just checking something. So how do you do this merging of the reinforcement learning technique with the matrix factorization technique? Very easy. You recommend an action is a category. You feed that category to the matrix factorization algorithm, and then you only recommend items from that category. The problem here is the following: if you guess the category, you increase the chances to have a hit, right? But if you miss the category, then your chances are 0. So, and this has a very negative impact, as you will see ahead. The clustering technique, basically we used k-means. It's a very simple approach. We only use very simple approaches. And this is the distribution of songs across clusters. There's quite a bit of imbalance. And we also show here the number of clusters per session, and the most sessions had 4 clusters in them, but there was a bit of a variance here. We evaluated this offline, completely offline. We didn't have access to an online system, and furthermore, the data set, as I said, the music tracks in the data set were anonymized, so we couldn't quite reproduce a user study. So we did this offline, and how did we do this? Well, we split this in the learning stage, in which the algorithm simply learns from the observational data, and then we pass to a recommendation stage, which is basically a test stage, in which we also perform learning while predictions are being made incrementally.
I'm gonna hold by the way.
Okay. So one important detail here is that for the reinforcement learning agent here, in the learning stage, we only have one Q table that is common to all users. We did this because it was sessions were quite small. It was very hard to do a personalized Q table. So in the learning stage, we have only one Q table. There's no personalization. But the matrix factorization algorithm is by nature personalized, so it learns normally. In the learning stage, we simply replicate this Q table through all users, and then we have a Q table for each individual user. Okay, since the Q tables are relatively small, this is feasible. So we split in 85% for the training stage and 15% for the test stage. So what we see here is the first results that we got. So as I said, if the reinforcement learning agent gets the category right, then you have a high chance of having a hit. But if it gets it wrong, you fail for sure. And this is what is reflected here. In the table above, you have the matrix factorization algorithm with the reinforcement learning, and you actually see that comparing to the matrix factorization alone, there is a drop in performance, which comes from this behavior. But if we account only for the cases where the reinforcement learning agent gets the category right, then you double the performance. So what we did was to use a hybrid approach and join and use basically what we did was use recommendations both from the reinforcement learning category and from the matrix factorization algorithm without any type of filtering. So we produced 4 recommendations, 2 of which are from each of the alternatives. And here we get a hit ratio of 10%, which is higher than the 7% originally, if you don't use this kind of hybrid strategy. And in the right, you have the 3 strategies, and you can see there is a considerable improvement. So I'm concluding here. This contribution is divided into components: a reinforcement learning-based sequential recommendation algorithm, and a hybrid algorithm that takes advantages of this, that recommends specific items taking into account the recommended actions. And results suggest that our proposal improves over non-reinforcement learning standalone methods. But there's a ton of work that needs to be done here. This was done in a very short time, a very short amount of time, and we only tried very simple ideas. So our next steps would be to experiment with other algorithms and modeling settings. For instance, the clustering algorithm could be. We can play around with clustering algorithms and settings. The reinforcement learning approach was very basic as well. We can try other alternatives, and the actual recommendation algorithm, the matrix factorization algorithm, was also very simple. We can use other more fancy stuff. We like to use this to different recommendation scenarios, but we have lack of data sets. So if any of you knows about a data set that we can use, I'll be happy to take advice. And we would like to test the evaluation, to evaluate this with real users, but it's quite hard because if the tracks are anonymized, you can't really create playlists and use the same data to model. Maybe we can do this with another type of data set, or maybe with with less data. And this concludes my talk. Thank you for listening. I'll be happy to take any questions.
Questions from the audience?
Thank you for the very nice talk. I like when you said about simple methods. There's a former colleague of mine who advocates for simple solutions that work really well. My question was around sharing information between the states after you have done the clustering with k-means. Are these states considered, as well as the action clusters, considered completely independent, or can there be information sharing for actions that are similar to each other or states which are similar to each other?
I'm not sure. In this approach, we have a simple Q table, and every possibility that appears in the data set goes into the Q table. So we don't exploit any type of similarity between actions or states.
Sounds good. Thank you.
Any other questions? No question. Was there a hand up? No. Any questions on Zoom? No? Okay, then, oh, wait, okay. Thank you, brave soul.
I was just curious how you came up with the weightings for the mean of like skip in this context is this much, skip in this context is that much. Because my experience working with this negative feedback, deciding how negative this negative feedback really is very difficult.
You were talking about the formulation of the reward, right?
That's right.
Okay. Well, this was completely arbitrary. I mean, we just came up with the values that we felt that were good. So the idea was to experiment with we actually did a small user study in the campus, asking for people what was the meaning of the skip in a certain scenario, and this is a little bit based on that. But we didn't study any different type of settings, so this is future work as well.
Okay, if no other questions, then let's thank Joel one more time for giving this talk. So now I think we'll break for an hour for the poster session and coffee. And then when we come back, Maria will be leading a exciting, very, very exciting panel discussion. And we'll be closing out the first day of the Consquences reveal workshop. Okay, I'll see you back here in an hour or so.